I'm Stephen A. Edwards from Columbia University, and I'm going to talk about the Sparse Synchronous model, a new real-time model of computation I've developed with my co-author, PhD student John Hui. As with most models of computation, this one started with rats. No, not New York's pizza rat, but lab rats. A biological researcher from Cold Spring Harbor Lab asked me for a better way to conduct behavioral experiments on his lab rats. He was measuring the rats' level of confidence by timing their responses to various confusing stimuli, although none achieved quite the level of confidence exhibited by the pizza rat. To do this, he would code a finite state machine in MATLAB and download it to a microcontroller running a cyclic executive with a 100 microsecond heartbeat. The tasks themselves were quite simple, but he wanted to do things like debounce the inputs from the skittish rats, so his FSM model quickly grew unwieldy. From my experiences with SRL and the synchronous languages, along with Ptolemy's tides model, I knew there had to be something better. But after looking carefully at each of these models, they didn't quite fit the problem. So we developed what I'm calling the Sparse Synchronous model, which is something like a discrete event model in which the behavior at each instant is governed by imperative synchronous style semantics rather than the non-deterministic concurrent semantics that you'd find in a more traditional discrete setting like Verilog or VHDL. I'm going to describe SSM in the form of a toy language. I don't expect anyone to code directly in this, but it will serve to illustrate the language primitives. SSM is built atop a traditional imperative language. For example, here's the classical GCD algorithm coded in SSM. There isn't anything especially novel here. I just want to show you that you're likely already familiar with SSM's basic semantics. A program consists of named routines that are executed purely for their side effects. They don't inherently return values, but that functionality can be recovered. Routine definitions don't nest. Routines may have named pass-by-value arguments. In this toy language, values are always integers, but that's not fundamental to the model. Arguments may also be passed by reference, which among other things enables routines to return values. SSM provides the familiar while loops, which need not be bounded. It also provides the familiar if-then-else conditional, as well as imperative assignment, where the value of a variable, here a copy of the argument b, is updated. When this loop terminates, the GCD is written to the pass-by-reference argument r, effectively passing the result back to the caller. SSM also supports recursion, which I show here in the form of the horribly inefficient hello world of recursion, a Fibonacci number calculator. Routines may introduce local variables that follow traditional scoping rules, although they may be passed by reference to a callee, which can modify them outside the scope in which they were defined. Calling routines is done at fork statements rather than within numeric expressions. These particular fork statements are just standard function calls. The first fork calls fib recursively and waits for it to finish before passing control to the second fork, which calls fib again. The first call to fib places its result in R1, since I'm passing that local variable by reference. The second call places its result in R, to which R1 is added before the routine terminates. That fork is more powerful than this shouldn't be surprising. In general, fork has the ability to start up multiple routines concurrently. As you'd expect, a fork terminates only after all of its callees have terminated. Here, the main routine fires off foo and bar concurrently. Now, if foo and bar are both passed a by reference, there's a danger of a race, which I consider completely unacceptable for SSM. For example, here are two routines that don't commute. Foo adds 2 to a, and bar multiplies a by 4. The order in which these two are executed does affect the outcome. I chose a rather blunt mechanism to eliminate this apparent race. Specifically, forked routines execute in the order in which they are called. So here, foo runs first because it is listed first after the fork. Then bar runs. Since a starts out as 1, foo adds 2 to make it 3, then bar multiplies it by 4 to give 12. Bar appears first after the fork, the execution order is reversed. Here, bar first multiplies a by 4, giving 48, then foo adds 2, giving 50. This rather heavy-handed solution means SSM does not specify true parallelism. One possibility for getting around this would be to add some analysis that can determine when concurrently invoked routines can't interfere and therefore can be run in parallel. Another alternative would be to enforce non-interference through a type system, such as how Rust does it. For the moment, this remains future work. Now let's get to the real point of SSM, the ability to control time. Here's the hello world of the embedded world, blink, which blinks an LED at 10 Hz. SSM provides delayed assignments, which schedule future variable writes. The new value is computed when an after statement executes and is written into the variable at the prescribed time. Here, both the value and the time delay are constants, but they may be expressions. The time delay must be positive, however, and not 0. Normal assignments can be used if you want an immediate update. The other temporal statement is wait, which blocks until one of the variables it is waiting on is written to. In this case, blink waits for a write scheduled by its own after statement, but you can also wait on a write from a concurrently running routine, or even a write to a variable whose value is supplied by the environment. Note that wait waits for a write to a variable rather than a change in its value. This deliberately differs from the discrete event semantics in Verilog and VHDL, which are ultimately trying to efficiently simulate continuous systems by responding only to non-zero derivatives. SSM, by contrast, treats variables as message communication channels, where it makes sense to distinguish between sending a single 42 and two 42s in a row. Such triggered by write semantics also makes sense for conveying pure events, that is, messages without a payload, where the type of the underlying variable is something like C's void. As an STRL, an SSM system is treated as if it executes instantaneously within an instant. So in this example, each update is exactly 50 milliseconds after the previous one. Here's the waveform this program generates running on a real microcontroller. The frequency is 10 Hz to within the tolerance of the crystal oscillator. Of course, real processors aren't infinitely fast and can be overloaded. When a time-consuming operation is inserted, such as a recursive computation of the 19th Fibonacci number, the system starts missing deadlines. However, note that this only affected the duty cycle of the output, not its period. Increasing the amount of work makes the effect more dramatic, and at some point you would completely overload the processor, but at least the period is consistent even when some deadlines are being missed. Let's talk in more detail about the temporal semantics of SSM. In SSM, time is divided into equal-sized quanta, which prevents Zeno-like behavior and allows us to model time as an integer. The size of these quanta is platform-dependent and hidden from the user. This means SSM has no equivalent to the pause of STRL or the pre of Lust. For reference, we've been using 1 microsecond for the quantum of time. Consider running the blink example. Assume the LED variable starts at 0. At time 0, blink starts executing at the while loop. Still at time 0, the first after statement runs and schedules the LED variable to become 1 at 50 milliseconds. As I mentioned, SSM assumes code runs instantaneously. In particular, something like the while loop does not advance model time. So when the after statement speaks of 50 milliseconds, it means 50 milliseconds from the model time, which is still at 0. Next, blink executes the wait statement, which blocks until LED is written. Model time now advances to the next event, here the update of the LED variable. At 50 milliseconds, 1 is written to the LED variable, which unblocks the wait statement. Execution continues at the second after statement, which schedules another update of the LED variable, this time to a value of 0, at 100 milliseconds. Finally, blink again blocks on the LED variable, allowing model time to advance. At 100 milliseconds, the process repeats. The LED variable is set to 0, which unblocks the wait, and the while loop repeats. Another write to LED is scheduled for 150 milliseconds, and the program suspends. Now, let's talk about how to implement SSM. To do that, I'm going to take you through this more complicated blink example. Again, we'll blink an LED, but this time with a more complicated pattern. Specifically, we'll start up 3 blinking routines with periods of 50, 30, and 20 milliseconds. The blink routine declares a local variable E that we'll use to generate events. The loop toggles the LED using a routine called toggle, schedules a write to the variable E according to the period that was passed to blink, then waits for the write event on E. Overall, blink repeatedly calls the toggle function once every period. Now let's start executing this program at time 0. When main starts, we create an activation record for it that will store its state. Routines need to be able to resume after they call children and after they block on a wait, so each activation record holds a program counter. In C, we encode a PC as a function pointer and a small integer used for a case label. Each activation record also includes a pointer to the activation record of its caller, which I'm not showing you here for main. Main needs to know about the LED argument, but because it is passed by reference, a pointer to it is placed in the activation record and its value is stored elsewhere. Finally, each activation record is a priority field that indicates the order in which it will execute in an instant. The topmost activation record has a priority of 0. Now we come to one of the critical data structures in our runtime system, the ready queue, which orders routines according to their priority. We use it to ensure children of a fork, such as the 3 blink routines, always execute in order, even if only some of them run in an instant. The ready queue starts life containing the main routine. The basic loop of our scheduler removes the highest priority routine from the ready queue and resumes it, beginning here with main. Main starts by forking the 3 copies of Blink. Each requires its own activation record with a stored program counter, a link to its caller, in this case main, a pointer to the LED variable, the period argument, and storage for the local variable E. Even though all 3 E's are created equal, I'm going to call them E1, E2, and E3 to keep them straight. The first Blink inherits its priority from main, but adds 2 zeros on the right because there are 3 children. These extra priority bits count up in binary. The second child has 0, 1 appended to its right. The third child gets 1, 0. The result is that children are prioritized by the order in which they were called. Furthermore, the first child's children execute before any children of the second child. When a child is forked, it adds itself to the ready queue. Once the 3 children have forked, main returns control to the scheduler, which again removes the highest priority routine from the ready queue and starts running it. In this case, the Blink child with period 50. The while loop starts, and toggle is called. This creates a new activation record for toggle, which inherits its priority from its parent, and receives a pointer to the LED variable. Toggle then runs, switching the value of the LED variable, and immediately returns, which deallocates its activation record. Next, the after statement runs, scheduling an update to E1 50 milliseconds in the future. In our runtime system, we store scheduled variable updates with the variable itself. Storage for a variable includes its current value, a pending value, and the time to update it. This effectively limits the number of outstanding updates to any particular variable to 1. Later, if another after statement schedules an update for the same variable, the previous event is discarded, regardless of the time at which the new update is scheduled to apply. We chose to do this in part to avoid a potentially unbounded accumulation of pending events, but it has another benefit. This eliminates any possible ambiguity from multiple updates being scheduled for the same variable at the same instant. While each variable knows its own future value, we also track all events in a global event queue, implemented with another priority heap. This queue lets us quickly determine the next instant in which to do something and what to do. We implement our event queue as a binary heap of pointers to variables, but I'll draw it as if the events were actually in the queue. Finally, the Blink routine waits on E1, which will illustrate the last main trick in our runtime system. To implement blocking on a variable, each routine owns some triggers in its activation record. Each trigger indicates the routine it can resume through a pointer that stays constant as the system runs. When Blink indicates it wants to wait on E1, it adds its trigger to the list of triggers for E1 and returns control to the scheduler. This prompts the scheduler to select the next highest priority routine from the ready queue, here the 30 millisecond Blink routine, and runs it. As before, this starts the while loop, toggles the LED, and schedules a write to E2 at 30 milliseconds. This event is also added to the event queue, where it becomes the earliest event. Finally, the second Blink waits on E2, adding its routine's trigger. The scheduler next starts up the third instance of Blink, and the process repeats. Finally, the system is done for time 0. Model time now advances to the earliest event in the queue, currently 20 milliseconds. The event is executed and consumed, which writes to E3. The write to E3 schedules the third Blink, since it is E3's list of triggers. Now, all the events at time 20 have been executed, and the third Blink routine is in the ready queue, so the scheduler executes it. When Blink awakens at a wait, it desensitizes its trigger on E3, restarts the loop, toggles the LED, schedules a write to E3 20 milliseconds in the future, that is, at 40 milliseconds, because model time is also at 20 milliseconds, and waits on E3, adding its trigger to E3's list. At this point, the system is done for time 20 and next advances to the next event in its queue, which is at 30 milliseconds. Here, the second Blink is triggered, toggles the LED, and schedules itself for 60 milliseconds. At 40 milliseconds, the third Blink schedules an update for E3 at 60 milliseconds, which is interesting because the second Blink has also scheduled an update for that time. At 50 milliseconds, the first Blink schedules itself for 100 milliseconds. At 60 milliseconds, something interesting happens because the queue holds 2 events at this time, one for E2 and one for E3. Events in the queue are ordered only by time, so the two updates for E2 and E3 are effectively unordered. However, the order here does not matter because the variables are distinct and the routine priorities that are placed in the ready queue are totally ordered. So let's assume the E2 event is consumed first. E2 is updated, and its triggered routines added to the ready queue, here the second blink. Now the E3 event is consumed, E3 is updated, and its triggered routines added to the ready queue, the third blink this time. Now we are ready to run the routines for the instant. The scheduler selects the highest priority routine from the ready queue, in this case the second blink, and resumes it. This causes the LED to toggle and an E2 event to be scheduled at 90 milliseconds. Once the second blink suspends for the instant, the scheduler takes the next routine from the ready queue, in this case the third blink, and resumes it, which schedules an E3 event at 80 milliseconds. The system is now finished with the instant at 60 milliseconds after it started. Now I want to talk about some of SSM's progenitors. We were heavily influenced by the TIDES model, which came out of Edward Lee's group at Berkeley and appeared in RTAS in 2007. Their basic idea, which we adopted for SSM, is to specify real-time behavior in the style of a discrete event simulator. As such, TIDES and SSM have a similar sparse model of time. We also adopted the TIDES technique of distinguishing model time, which the program can observe and control, from physical time, which the runtime scheduler uses as a reference for model time. However, SSM differs from TIDES in many important ways. One of the most important is SSM's use of a different execution model within an instant. While TIDES effectively does event-driven simulation within an instant, which requires them to go to heroic but ultimately insufficient lengths to ensure deterministic behavior, SSM employs its own totally ordered execution semantics within a single instant that guarantees determinism. Another big difference is SSM's support for dynamically changing topology through function calls. TIDES, by contrast, assumes the communication structure of its systems remain fixed throughout their execution. While this makes TIDES systems easier to analyze, it precludes many types of algorithms. TIDES has one very clever advantage over SSM, the ability to support distributed implementations. By carefully analyzing delays and silences, a TIDES system can be implemented in parallel while still respecting its discrete event timing semantics. This is described, for example, in Jia Zhou's 2011 PhD thesis. Because our models are similar, we hope to adapt the TIDES technique to SSM, but this remains work in progress. I've been working on STRL since 1994, so there's very little of mine that it hasn't influenced. But Gerard Barry has been working on it even longer. Determinism is my favorite property of STRL, which I insisted on for SSM. Like STRL, the output behavior of an SSM system is a function purely of its inputs and not of the speed or behavior of its runtime system. The main thing I wanted to get away from was STRL's insistence on doing something in every instant. STRL models time as an abstract series of instants. This can be linked to real time by providing clock inputs that signal time advancing, but this tends to lead to a heartbeat implementation style. STRL semantics make it difficult for a runtime system to conclude that nothing needs to happen for, say, 15 milliseconds, and set a hardware timer accordingly. The ability to reason about time as a number and use hardware timer interrupts was a key design goal for SSM, which we achieved by making time less abstract than in STRL. Unlike discrete event models like TIDES, STRL directly tackles the problem of simultaneous events by applying principles from constructive logic to reason about which signals must, may, and will not be emitted in an instant. This gives STRL its determinism, but at substantial cost. One direct consequence is that there doesn't appear to be a way to compile an STRL program as separate modules. SSM, by contrast, makes separate compilation easy. Linking is no more difficult than in C. SSM's runtime's use of priority queues makes it more dynamic than STRL's typical insistence on completely static scheduling, although I and others have developed a spectrum of efficient implementations of STRL. Finally, STRL's need for static scheduling and whole program compilation precludes things like SSM's true recursive function calls. Some proposed extensions to the STRL model also inspired aspects of SSM. Sequentially constructive concurrency, due to our old Reinhard von Hochslinden and his posse, relaxes STRL's rigid single value per instant rule in straight-line code, or more generally, when you can uniquely determine the order of writes and reads. I think of SSM's variables and children run in order rules as embodying the spirit of sequentially constructive concurrency. The idea of dynamic ticks, presented at FDL in 2017, is to equip SRL programs with the ability to specify the physical time at which the next instant will occur. This powerful idea is also at the heart of SSM, whose semantics are built around a similar wake up, do work, set the next wake up time model. SSM, however, goes one step further and provides the when to wake up machinery in the form of an event queue. The dynamic ticks paper merely suggests the user implement such a policy herself. Frédéric Boussinot's work, including Reactive C, Fair Threads, and most recently Funloft, like SSM, provides concurrency through lightweight cooperative multitasking and has an SRL-like model of time based on logical instance. SSM also adopted Boussinot's approach of using the order in which parallel functions are called to dictate the order in which they are executed to resolve potential nondeterminism. The big difference is that SSM routines are executed at most once per instant, whereas Boussinot executes them in round-robin order until they converge. Both techniques are ultimately deterministic, but SSM's policy makes it easier to predict per instant execution time, and we feel SSM's behavior is easier for programmers to understand. In summary, I presented the Sparse Synchronous model, a new real-time computational model that treats time as discrete instance, uses discrete event semantics to schedule operations between instants, and imposes a simple, totally ordered semantics within an instant to provide deterministic behavior. I presented SSM in the form of a toy language built from a basic imperative core extended with the ability to schedule future variable writes, block on variable writes, and concurrent routine calls, which may even be recursive. I explained how to implement SSM with a runtime system that manages two priority queues, an event queue that tracks future variable updates, and a ready queue that manages the order in which routines are reactivated in an instant. Suspending a routine to wait for a variable write is a key facility of the runtime. When a routine chooses to wait on a variable, it adds its trigger to the variable's list of triggers. When a waited-on variable is written, the routines waiting on that trigger are added to the ready queue to be run later in the same instant. All of this is done in bounded memory, provided the recursion depth is bounded. Then I explained how SSM combines notions from the p-tides model, the SRL synchronous languages, with extensions including sequential constructive concurrency and dynamic ticks, and the works of Boussinot. The runtime system I described here is available on GitHub under S. Edwards Lab SSM. We are currently using this runtime system as a compilation target for an imperative language that extends the toy language I presented. I used this to code the demos I showed running on real hardware, such as this one.